It doesn't matter how beautiful your theory is. It doesn't matter how smart you are. If it doesn't agree with experiment, it's wrong. Richard Feynman. Wow. When you want to talk about the weak force, you have to ask, how are you going to see it? Beta decays are one of the ways that we have observed this force of nature, and there is an associated process that is in the early days was extremely speculative, and nowadays it's becoming a kind of a big part of the story of studying the weak interaction. It's a story of neutrino. Neutrino is a particle of the nature, like an electron or proton. It's another one of those fundamental particles. This particle is completely bizarre for the simple reason that it only feels a weak force. Okay? Imagine a particle with no electric charge, so it doesn't feel electricity. It has no mass. Okay? That's a very weird concept. I'm talking about the particle with no mass. How can that be? Well, we've met a particle with no mass already. It's a photon. The photon, the carrier of electricity and magnetism, is itself a particle with no mass. Again, the photon, the carrier of electricity and magnetism, is itself a particle with no mass. We have seen it before. It's kind of hard to visualize, but there you go. It's what you have to postulate in order to make sense of the experiments. So it has no mass and no charge, and it has no interaction with the proton and the neutrons. No strong interactions. It can just go whizzing right through the middle of the proton, and it doesn't care because it only feels a weak force. That means that it can only emit and observe W or Z bosons. Which is highly improbable event. So most of the time, the neutrino just cruise through the matter and don't interact. It's like a ghost, right? Transparent, intangible ghost. Let me tell you a little bit about the sort of origin of the neutrino. How on earth could we have come up with this crazy idea for a particle that nobody can see? Of course, nowadays we can see them, but in the early days we couldn't. The inventor of this particle, and I use that word, sort of the Lucy. I mean, you don't invent a particle. Nature has the particles. I don't know. You discover the particle like the Wolfgang Pauli. Pauli was a remarkable physicist. He was one of the generation. He was over a generation that was developing quantum mechanics. Mr. Schrödinger and Mr. Heisenberg had invented the theory of quantum mechanics, but Wolfgang Pauli was really one of the big key players to turn the theory from the fielding idea into the robust, well-developed mathematical framework. Right. Mr. Pauli was the one who figured out what we call the Pauli exclusion principle, that say that two elements can't be in the same place at the same time. It may seem obvious, after all, how could you put two particles on top of each other? But this was a very important idea in the development of the quantum mechanics. In fact, that idea that two electrons can't be in the same place is what's responsible for chemistry. Chemistry, yes? Again, in fact, that idea that two electrons can't be in the same place is what's responsible for chemistry. Right. So Wolfgang Pauli's work, really that's what he got his Nobel Prize for. This understanding of the chemical properties of the elements boils down to this. If you start adding electrons to some nuclear system, so the electrons go into orbit, the first one goes down into the nice and low, stable orbit. Remember, electrons have spin, and so an electron can be spinning clockwise, or it could be spinning counterclockwise. Quantum mechanically, those are two different states of the matter. Clockwise spin, counterclockwise spin are distinguishable, different states. So Mr. Pauli says, You can actually put two electrons right next to each other if their spins are in opposite directions, because they are different from one another. You can put different things together. You just can't put identical spin one half protons together. A helium atom has two electrons, and that's a nice and stable. They are both down in this low orbit. But what about lithium, which has three electrons? You add the third electron and it's not allowed to go down into that same orbit because it's got a spin one half. I see now! It could be a clockwise or counterclockwise, but it can't be either down where the other ones are. So let me repeat it again because this is so important. They are okay. What about the helium? A helium atom has two electrons, and that's nice and stable. They are both down in the low orbit. But what about lithium, which has three electrons? You add the third electron and it's not allowed to go down into the same orbit because it's got a spin one half. It could be clockwise or counterclockwise, but it can't be either down where the other ones are. So it has to go into some more loosely bound orbit, which means that lithium has a loosely bound electron. It's very chemically reactive, so this is a way that we begin to understand chemistry from the understanding the physical principles. Yes, sure. Mr. Pauli was responsible for lots of amazing developments in the quantum mechanics, and one of his idea, perhaps his most tentative. He was a little bit afraid of the idea. Was in response to the looking carefully at the beta decays. So imagine the simplest beta decay. It wasn't actually the one that Pauli was considering, but think of the neutron sitting in the laboratory. You could watch it. You might have a little emulsion or bubble chamber image of the neutron just sitting there, and then poof! It decays and turns into a proton and an electron. Now, if you are measuring data like that, you can very carefully measure the original energy of your system and the final energy of your system. You have to use Einstein's E = mc square to figure out the initial energy, and in the end, you've got a E = mc square. You've got the rest mass energy of the proton and electron. You've also got some kinetic energy of motion. You have to add it all together very carefully, and when you do, you discover that there is more energy to start with than you have in the end. That's kind of the scary idea. To Wolfgang Pauli, it was a completely unacceptable possibility. Conservation of energy is a deep principle of physics, of course, and so he's asking himself, how can this be? How can energy just disappear from nature? Right. Momentum is also not conserved. Momentum is a fancy word that means the oofs. Yeah, oofs. So if you start off with a neutron and it has no oofs, it's just sitting there. It has energy, but it has no motion. Now it creates a proton and an electron, and oftentimes they go off together. You know, one goes in one direction and the electron might go in a similar direction. This is really weird. You'd expect if the proton goes one way, the electron would have to go back to back, recoiling against it to keep the total momentum conserved. But again, it's not seen in the experiments, so this is a usual story. You've got some experiment that doesn't agree with some fundamental principle of physics. You had a choice in the 1930s. Actually, it was in 1930 when Pauli came up with this idea. When you could abandon conservation of energy. Really? when you could abandon the conservation of the energy and conservation of the momentum, but a slightly less radical proposal would have been to imagine that there was another particle involved. But yeah, that's the point. Yes. But a slightly less radical proposal would have been to imagine that there was another particle involved, a third particle. He didn't actually name it. It was named later. This particle was the Neutrino. Neutrino. It could run away as well, carrying energy and momentum, and that would preserve these conservation laws. It's just another particle. Nowadays, we propose new particles all the time. It's not a big deal in this generation. But in the 1930s, this was 1930. It was before the discovery of antimatter, before the discovery of the muon, and even before the proposition of the pion. This would really be the first new particle proposed, and it was just too scary, yes. Wolfgang Pauli didn't publish a paper about it. He wrote a letter to his colleagues at the conference. He began the letter, "Dear radioactive ladies and gentlemen." He had a good sense of humor. Pauli was an amazing fellow. People sometimes call him the conscience of the physics. Conscience of the physics, because he was so smart and so sharp. Not mean, just sharp. When people would relate ideas, he was very quick to criticize, but in a scientific manner. So clever, so respected, right? There is a famous quote of him at the meeting. He says, "What Professor Einstein has just said is not so stupid." This is sort of the typical Wolfgang Pauli. He had a big ego, and it's sort of interesting to speculate as to why didn't he publish his idea about the neutrino. I think it's because he was so critical of the other wild ideas that he was a little bit timid about proposing his own wild idea. What irony. In fact, here is another quote from Pauli. "I have done a terrible thing. I have postulated a particle that cannot be detected." Okay? Think about why that's such a terrible thing. This is a physicist. Physicist is about measuring stuff, okay? So we can talk all we want until we are blue in the face about elegant theories and beautiful mathematics, and nowadays that actually carries some weight. But even nowadays, ultimately, it doesn't matter how beautiful your theory is. I don't care how elegant and formal and lovely and consistent the mathematics is. It's only physics if you can go in the lab and verify it, right? That's the essence of the physics. You have to be able to check these things. You want to see little tracks in the bubble chamber that proves that your mathematical proposition is correct. What Pauli was proposition was a particle of nature with no electric charge, so it didn't create ions in the bubble chamber. It had no mass. It had extraordinarily weak interactions. Once it was produced, which was a low probability event, it just cruised through matter and left no trace of itself. So this was a particle that was extraordinarily difficult, but not impossible, alright? It had a low probability but not zero probability, so in principle he could detect a neutrino. But in the practice, Pauli knew that this would be essentially impossible with the 1930s technology, right? So the idea was out there in the literature, and another physicist, Enrico Fermi, yes, Fermi estimates. Enrico Fermi took the idea just a few years later. He thought about it and developed it into the mathematical framework. Not just the idea of the particles, but really consistent mathematics. He describes the interaction of the neutrino with neutron, with the photon, and with the electron. With that, we have a mathematical framework and we can start calculating the probability of various different kinds of the beta decays. There are lots in nature. Every nucleus, in principle, can beta decay. Now we have a theory, so we can do calculations and they work. They work like the champ. So Mr. Fermi's theory is telling us that, yeah, you have to assure a neutrino for his theory to work, and then you start to agree with lots of data, not just the original one. There are other events that didn't involve the neutrino and protons. For example, remember those crazy muons? Who ordered that, right? The muon was this particle observed in the cosmic rays. It appears to be some sort of the heavy electron which would occasionally decay into an electron. It took a long time. It was a weak decay and an improbable decay. Fermi's theory actually allowed you to calculate the lifetime of the muon, and it worked. It was consistent with all other data. So in fact, according to the Mr. Fermi's theory, when a muon decays, not only does it produce an electron, it produces the two neutrinos. Wow! The story fits in consistently and mathematically, and this, allows people to believe in the reality of the neutrinos. But still, I think deep in our hearts we wanted to see one, and it took over the 25 years. It was in the 1956 that Cohen and Lenin's two physicists working outside of the nuclear reactor were able to do so. What they did basically was that they stood outside of the nuclear reactor because nuclear reactors produce lots and lots of the neutrinos. Just as the sun does. A nuclear reactor is a primary strong car that emits neutrinos. When the reactor was on, it was just spewing neutrons like crazy, which just went flying off, interacting with nothing most of the time. Cohen and Lenin's set up a giant detector outside of the facility, right outside, really big. So there were lots and lots of the target atoms, target nuclei, and so, they had a low probability event with lots of chances. Wow! It was like a rolling dice over and over and over and over again, and once or twice an hour they would see an event. It was called Project Poltergeist. Project Poltergeist, because they were looking for these little ghost-like particles. They found them, and when the reactor was off, they got nothing. Wow! When the reactor was on, they would get 2 events an hour. They won the Nobel Prize for this work. This was a direct evidence, alright? You see, it was a sort of an opposite process. Instead of producing a neutrino, the neutrino came in, right? Walked into the neutron and created a particle. Actually, it walked into the proton and created a particle. How do you make sense of the particle with no mass and no charge? It's hard to picture, and I think you just have to look at the mathematics and at the calculations, and you realize that the prediction of this particle consolidates an enormous amount of the physical data in a simple way. So you have to do the mathematics, right? Yeah, that's why I'm doing the mathematics, in order to figure out really what's going on, in order to make myself understand the things that people know. You take one prediction, one theory of Mr. Fermi's, and then you can essentially make an enormous number of generalization to whole bunch of different circumstances. Right. We call those leptons. That's just a fancy word which means light particles. Although later on we've discovered leptons that aren't so light anymore. But in those days we are classifying the particle and trying to organize this world of the subatomic particles. The electron, the muon, and the neutrino are kind of all in the family together. They do not interact with protons and neutrons in a strong way. The electron has electric charge, so it can interact with a proton electrically. The neutrino feels only the weak force, and they are somehow connected. As we progress in this course, we are going to talk more about the connections among muons, electrons, and neutrinos. Neutrinos have spin, just like the electron did. They have a spin 1/2, which means they have a certain amount of the angular momentum. In principle, that means they could spin clockwise or counterclockwise, and it's an interesting fact of nature, which we'll be again talking about in a future lecture, that every neutrino that we've ever found always spins the same way. Antineutrinos, which also exist, spin the other way. According to the Mr. Dirac, every particle should have its antiparticle. We are going to have to talk about the story, because that's definitely not the same as the electron by any means. Wow. Right. It's also the case that neutrinos are rather rich in the following sense. If you have a beta decay that produces an electron and neutrino, that neutrino have some property, some character of the electron in it. Wow. We call it an electron-flavored neutrino, because it was created in a partnership with an electron, and as it cruises along, it retains that property, that characteristic of being an electron neutrino. It's one of the ways that you describe your particle. Do you have electron number? Even though it's not an electron, it's associated with the electron. What that really means is that if it walks into the nucleus later, a low probability event. But if it does interact weakly, then what it will produce is an electron, or maybe an anti-electron, depending on the whether you have a neutrino or anti-neutrino. It will never produce a muon. There are other neutrinos that have been discovered in more recent years that are muon-flavored neutrinos. So, for instance, when the muon decays and it turns into the electron, it produces the two neutrinos. One of them is an electron-flavored neutrino, and one of them is a muon-flavored neutrino. So you can actually create beams nowadays of the muon-flavored neutrinos or electron-flavored neutrinos. If you have a muon-flavored neutrinos beam and it walks into the target, again, a low probability, but if it does have this weak interaction, it will always produce a muon, never an electron. So it has this character to it, and nowadays one of the puzzle about neutrino is whether there are any big probability of an electron-flavored neutrino turning into the muon-flavored neutrino. It's completely weird idea, and we'll come back in the future lecture, which will be devoted to the topic of neutrinos, right? They are fascinating particles. I don't know why I don't know why I find them so interesting. You know, there is a saying that it's like a love and antiques, yeah. So you know, there is a saying that it's like a love and antiques. If something's hard to get, then it's interesting, and neutrino are so hard to get. They are hard to measure and they are hard to detect, but it is possible, and we are getting better at it. Maybe it's because my dad called me Steverino when I was a little kid. I don't know. These particles are, in some sense, the most esoteric, wispy, ghost-like particle I could think of. But nonetheless, we have actually come up with applications for these things. People have thrown around ideas and asked if there are any technological uses for the neutrinos. Kind of at least it was the whimsical question. I mean, people were making jokes about communication from the submarines because the neutrinos would travel, all the way through the planet Earth without interacting with anything, and you'd have some giant detector. But that's a fairly ridiculous idea, at least for the present day. What we have done with the neutrino already is that they are produced copiously in the sun. Every nuclear reaction in the sun produces a neutrino, so the number of neutrinos coming out of the sun is astronomical. Yes, astronomical. Yeah, this is pretty much astronomical. There are about 100 billion neutrinos per square centimeter. That's the size of your thumb or your eyeball, passing through every square centimeter of you every second. Most of them are coming from the sun, some of them are coming from stars, and even from the early universe. Whoa! And they are just passing through your body. During the dynamite, they are coming through the roof of the building. If you are inside of the building and in the direction of the sun, most of them passing through you, going through the earth. The people who are on the other side of the earth are sleeping right now because it's nighttime over there, and the neutrinos are coming up from underneath the floor, through their bed, through them, and off out into the outer space. Wow! The same number, 100 billion per square centimeter per second. These solar neutrinos, these astronomical neutrinos are very low energy and stupendously difficult to detect, but we have detected them. Wow! And that's going to be a future story as well when we ask how we do that. Now, we have actually seen an image of the sun, if you like. It's like a photograph of the sun, but not in the sunlight, but in the neutrino light. So we have actually seen the sun by detecting the neutrinos that comes from it, and we have even seen a supernova which occurred a long time ago, hundreds of thousands of years ago. It was in 1987 that we saw the light from that supernova, and at the same time we saw a few of the neutrinos from that supernova. Now, why is that interesting? Well, neutrons come from the center of the sun, where the nuclear reactions occur. The light from the sun comes from the outside edge. We have no way of seeing the inside of the sun. There is no way anybody could imagine of getting inside the center of the sun except through the neutrinos. So they are like this microscope that looks inside to the center of the sun or supernova or the center of our galaxy. A wonderful astronomical tool using these exotic particles. Wow! Thank you!